Okay, thank you so much, Chris, for the introduction. Thanks to my two esteemed colleagues who went before me, and thanks to Twanadal for allowing me to speak today. So as Catherine just nicely put it, there's some of us who are, I guess, smug, and some of us who are embarrassed. That just moved. I'm one of the embarrassed ones, so I'm going to dive into it. And what Catherine talked about is a really good introduction for what I'm going to get into today. So this is going to be a distance ladder of photometry to measure the expansion rate of the universe. Okay, so I'm going to actually do this talk kind of in reverse of maybe how I normally do it, and kind of quickly talk about this Hubble tension, which Catherine mentioned, and then use that to talk about something simple. So as you can see, this nice cartoon from XKCD, it summarizes the issue that there are two main estimates of the universe expansion rate, and they disagree. So measurement of star distances, this is what I work on, suggests the universe is expanding at 73 kilometers per second per megaparsec. And measurements of the cosmological background suggest it's expanding at 68 kilometers per second per megaparsec. So these are the kind of two numbers of the values for the Hubble constant. And kind of it's important to note that my team, which is the SH0ES team, is measuring this directly, whereas another team, the Planck team, which Catherine talked about, is measuring the universe when it's very young from the cosmological background and inferring what the Hubble constant should be today. So it's really kind of our standard model combined with a measurement of the universe when it's very young. Okay, so this is the tension, and it's now 5 sigma. And I'm going to, since this is a photonics conference, I'm going to talk about this just in respect of how do we actually measure how bright objects are in the sky, which sounds like a kind of simple question, but it's very complicated, especially when we're dealing with these possible discoveries. It's extremely important. Okay, so just kind of quickly to give a few shout outs. There's a number of papers that just came out really in the last month or two. A number are led by grad students here at Duke and around the world. Just kind of naming a couple of my top collaborators. There's Dylan Brout from the Pantheon Plus team, Adam Reese from the SH0ES team. And this work is really kind of combining these two teams. Okay, and if you're curious about this, I just kind of want a long explanation of all the different facets. There's a really nice article that came out. This is by a guy who writes for Forbes. His name's Ethan Siegel. And yeah, one nice thing he says, just to pull out a quote, since I can't quote so well about myself, is it's arguably the most impressive of all the heavy lifting done by the Pantheon Plus team, the remarkably tiny errors and uncertainties that exist when you look at the data. And today I'm going to talk about kind of how we actually can trust those tiny errors and uncertainties. Okay, so this is a diagram, a plot of what we call the distance ladder. And there's 3 rungs. You can see three kind of panels here of how we're measuring the expansion rate of the universe. In the first rung, we are using some method like that's geometric. So this is like parallax, or using some kind of interesting binary star system with water masers. So this is a geometric scale, and you're essentially calibrating the luminosity of Cephids. And this is all happening for objects relatively kind of nearby for us. Then in the second rung, you say, okay, now that I have calibrated the luminosity of Cephids, let me find galaxies where there are exploding stars called type 1a supernovae, SH0ES. And since I know the luminosity of the Cephids, then I could infer the distance to those galaxies, and then I could infer the luminosity of the supernovae. And then the third rung, you say, okay, now that I've measured the luminosity of the supernovae, let me look at galaxies that are moving away from us. And basically there's a degeneracy between how fast is the expansion rate of the galaxies away from us and the luminosity of the supernovae. So if you've figured out what the luminosity of supernovae is, then you can measure the expansion rate of the universe. And what's kind of really key to this whole thing is consistency between rungs. So basically how you measure the Cephids should be the same way. How you measure the supernovae should be the same way. And as long as you do that, then our result will be robust. So essentially what we're doing is we're comparing brightnesses of Cephids in the first and second rungs, Cephids that are kind of close to a little bit further away, and you're comparing supernovae in the second and third rungs, supernovae that are close compared to far away. And the result that we get is really that delta, that relative measurement once you've tied it to some geometric method. Okay, so this is what Catherine showed. Basically, our team gets an H of 73 plus or minus 1. This is now at that kind of famous 5 sigma level from Planck. This could possibly imply that there is some really exciting new physics that is waiting to be discovered. So there's a nice compilation of results from Eleanor Di Valentino et al. And she's showing here a number of different solutions of a new kind of dark energy or axions, and kind of there's no shortage of papers now of what could explain it. Kind of there's not really one that's great, but there's some kind of particular excitement in the early dark energy sector. Okay, so I want to kind of now get into how we actually do the measurement, and really there's multiple steps. I'm not going to talk about all of them. You have a supernova go off. You have to kind of model how you've discovered that supernova, how you've measured that supernova. We have to kind of measure how fast the galaxy seems to be moving away from us, and we have to measure its distance. But really, I just want to focus on 2 parts of this process, which is that we're observing these supernovae with multiple telescopes over many years. And the supernova will go off in a galaxy, and we don't want to measure the galaxy light. We just want to measure the supernova light. So I want to talk about how we do both of those. Okay, so the first question is, how do we define a magnitude system for stars in the sky? And how do we calibrate observations from different telescopes that are 40 years to agree? And so basically, we have all this amazing data from the community over now 4 decades or so of different supernovae. How do we kind of use it and compile it and leverage all of that data? Okay, so the first question is, how do we just decide, how do we agree on some kind of photometric system? And so I thought this would be interesting to this group because it's not an obvious question. So there's 2 real methods now. One is basically to use special stars called white dwarfs, where their physics is kind of relatively simple, and allow those to be your primary standards. Basically, those are your kind of fundamental building blocks of kind of, if white dwarfs have these properties, they have these temperatures, they have these brightnesses, that sets basically the magnitude system of every other observation you do in astronomy. So this can now be done, I'd say, kind of pretty well. It's on the level of like 0.5% for 7,000 angstroms. But the issue is that if you're saying, okay, white dwarfs are my truth, then you better be sure that you can model white dwarfs. And this plot on the right is from Bolin et al., which is showing kind of 2 different ways of modeling these special stars. And you can see kind of 1 to 2% differences in the models. So if you're kind of saying these are our primary standards, but actually kind of how well we can model them is not so great, that's a problem. Still kind of say this is method number 1. This is currently what we're using. And there's a lot of work kind of on the modeling side of how to improve this, but this is a serious limitation. Okay, the second method is basically to say, forget about anything that's going on in the sky. This is kind of going back to kind of the first talk that we heard about supermassive black holes, and saying, kind of like with using lasers, use your system itself to determine a magnitude system on the sky. So basically, if you can know the efficiency of your system, the edges of your filters, if you can know the throughput of the atmosphere, which is really hard, and you can basically say, I understand my system well enough that whatever it's seeing, it's kind of seeing in some absolute counts, and you basically kind of project that onto your observations of the sky. So this is this metrology idea. It kind of hasn't worked as well as the white dwarf idea, but kind of for this next generation of telescopes, this is the hope. So we now can kind of do this to about the first plan to about 1%. This other idea about the 2 to 3%. Okay, so then there's the question of, all right, well, you have different telescopes and they are observing different supernovae at different times. How can we put this all part of the same data set? And what's nice now is that you have multiple telescopes that are doing large sky surveys where they're looking at a number of stars. And we could basically just compare the magnitudes of stars across the sky. So this is a comparison by this paper by Eddie Schauffele and Doug Finkbeiner et al. using comparing Panzer's telescope and the Sloan Digital Sky Survey, and it's just looking at for any kind of systematic differences across the sky. And what you could see here, this is in different bands, kind of where like the heat is in millimegs. And basically what you should be able to see is just stripes. And those stripes are because Sloan observed with a kind of a stripe pattern. Basically, that's how it slewed across the sky, essentially. So Pan-STARRS in this sense was good enough to show the Sloan observing strategy, which showed the Sloan problems in their calibration. So basically, if you have enough stars observed by multiple telescopes, then you can cross-calibrate the two and correct for problems between different telescopes. So one thing that I worked on is basically trying to invert this idea and say, okay, what if we have, instead of just 2 photometric systems, Pan-STARRS and Sloan, you had 20 systems where everyone says, hey, we know what our throughput is. We think we know what our throughput is. We think we have good observations of stars, and other systems, they think that they have measured their throughput well also, and they've looked at the same stars. Well, you can compare basically predicted or synthetic differences of the same stars to the actual differences of the observations of those stars. So on the left here, this is showing basically throughput versus wavelength for a number of different filters of a number of different systems. And on the right, this is showing basically how we have a number of observations of the same stars, but from 2 different systems. In this case, this is just Pan-STARRS and Sloan. And in black, this is showing the actual stars, the actual differences between observations of stars. And orange, this is showing the prediction. And basically we say, hey, if everyone did everything right, the observed should be on top of the prediction. And if you're not on top of the prediction, we can correct all the different systems and basically recalibrate all of the different observations over the last 40 years. So what essentially this looks like is we could say each system for each filter, what you're looking at on the right here, is off by 1 or 2% specific to a filter and system. And we could correct for that, basically creating a homogeneous calibration for 20, 30 different telescopes over the last 4 decades. Okay, so that's kind of idea number 1. Idea number 2, or question number 2, is how do we measure the supernova brightness, which is it's 1, changing with time, and 2, next to a galaxy or on top of a galaxy, very much near the core of a galaxy. So on the left, this is just showing some random supernova 2001 EL. It's close to galaxy light. Some are further kind of from the core, some are closer. It all depends. And basically the flux itself is changing. So this is on the right showing light curves where the flux is changing with time. And basically from these light curves, that's how you infer the distances, which is key to measuring the Hubble constant and for all this Hubble tension. Okay, so there's kind of 2 methods for this. And one is called difference imaging, one's called C modeling. So this just shows an example of difference imaging, which I'm sure kind of in a number of different areas, there are similar techniques. Where basically you have what we kind of call the search image, and then you have a template, which is some usually deeper image of the sky from a year ago or 2 years ago. So this is a plot taken from a paper by Duke postdoc Bruno Sanchez. And essentially what you do is you convolve the template image to look like the search image, and you subtract the 2. So this is image subtraction. And then basically the differences between the 2 are either artifacts, which happen due to satellites or quality issues with your images, or supernovae. And that's essentially what you're looking for. The other idea, which I'm not sure if people use as much, is what we call scene modeling, which is essentially you can create a pixelized grid of your underlying galaxy model, and you can convolve that with the point spread function of each night that you're observing, or the seeing, or kind of whatever kind of causes your signal to blur. You add that to any kind of background noise, which we're calling the sky, and then for every night that there's a supernova, you have a kind of fake image, which is the supernova flux plus your convolved galaxy flux plus the sky, and you compare that to your data. And you do this with a giant MCMC. It's very expensive, but the advantage is that it's kind of really exquisite control over the photometry that you care about, which is what's happening with the galaxy right where the supernova is. So essentially, this kind of shows some math if people cared about this. You're essentially kind of solving this chi-squared here, which is you have your data, some pixelized grid right around your supernova. Then you have your scene model, and you're looping over all the pixels in your stamp and all of the epochs that your supernova is in. So kind of, if anyone's curious about this more, you could search for scene modeling supernova and you can see this, but it works really nicely. So just kind of show an example. So on the left,
just to let you know, you've got 4 minutes.
Great. Okay, on the left here, this is what it looks like with data where this is what we call a stamp. There's a galaxy and then you have the simulation, and basically we solve for the underlying model. And basically, if you do this okay, then what you have is on the bottom right, the data stamp minus the sim stamp, and you see some supernova left. And that's kind of the things that you're solving for. Okay, so what you could do with this is that you can inject a number of fake supernovae into your pipeline and measure kind of how accurate your pipeline is. So there's another nice plot by Sanchez et al. You could also look at the efficiency of your pipeline in different filters. And all these things are kind of really important for measuring the distances and any possible selection biases. Okay, so just kind of to quickly say, we actually do the same thing for the Cepheid side. So these are galaxies that host Cepheids. Let's kind of show this with red dots. So all the red dots here are Cepheids of galaxies, and you can see that basically these Cepheids are just in the galaxy, and it's very tricky to disentangle the Cepheid light from stars near the Cepheids. So it's the same problem, but we actually do the same technique where you have a Cepheid, and then you have all these stars around it, and we do the same scene modeling where instead of having a galaxy, you have multiple point sources of all the stars around the Cepheids, and you kind of forward model them all at the same time with essentially like a big MCMC. And you can see that in this plot that you have some cases where your Cepheid is kind of in a crowded region, or somewhere it's kind of not so crowded, so less difficult. But both of them, essentially, we could propagate, we get the same Hubble constant. So I'd say kind of one last thing, which is that kind of for all these different photometry techniques, basically they do not end up changing the Hubble constant, even though they're super important and there's a huge kind of subfields devoted to this. And just kind of the last thing I'll say is that while we kind of are okay right now, basically the level of difficulty that there will be for these types of measurements goes up by a factor of 10 for this next generation of telescopes that Catherine mentioned. So this is just showing the field of view of the Roman Space Telescope. And then on the right, this is showing kind of all of our calibration requirements. And basically anything that's to do with the optics or photometry is just well beyond kind of what we're doing right now. So this is just going to be a huge area coming up. And I'll stop there. Thanks.